Okay, welcome everyone. This is Tech Tutorials. Today we are going to discuss about the stress-strain diagram, true stress-strain and engineering stress-strain relationship in detail. Please don't forget to subscribe to our new channel. Stress-strain diagram. The strain-stress diagram, also known as the stress-strain curve, is a graphical representation of the relationship between stress and strain in a material. It provides valuable information about the mechanical properties and behavior of a material under load. Let's discuss the components and regions of a typical strain-stress diagram. First, let's consider the critical points located on the stress-strain curve. Point A indicates the proportional limit, which refers to the maximum stress that a material can withstand without deviating from Hooke's law, which states that the stress is directly proportional to the strain within the elastic deformation range. In other words, the material behaves elastically and returns to its original shape once the applied stress is removed, as long as the stress does not exceed the proportional limit. Point B on the diagram indicates elastic limit, which is the maximum stress that a material can endure and still return to its original shape after the applied stress is removed. It is similar to the proportional limit but represents the upper bound of the material's elastic deformation range. If the stress exceeds the elastic limit, the material undergoes permanent deformation. Point C on the curve shows upper yield point, which is the stress point at which a material starts to exhibit significant plastic deformation. It is the point where the material's behavior transitions from elastic to plastic. Beyond the upper yield point, the material undergoes permanent or plastic deformation even after the removal of the applied stress. Point D shows lower yield point, which is the stress point below which a material exhibits a small amount of plastic deformation. It represents the stress at which the material begins to yield but does not exhibit significant plastic deformation. In some materials, the lower yield point is not well defined, and plastic deformation starts directly from the elastic range. Point E indicates beginning of strain hardening, the point at which a material's plastic deformation becomes more difficult. After the material passes the yield point, it enters the strain hardening region, where an increase in stress is required to induce further plastic deformation. The material becomes stronger and more resistant to deformation during strain hardening. Point F indicates ultimate stress point, also referred to as the ultimate tensile strength, is the maximum stress that a material can withstand before it fails or breaks. It represents the peak point on the stress-strain curve, beyond which the material experiences necking, localized contraction, and subsequent failure. Point G indicates fracture point is the stress point at which a material breaks or fractures. It is the point where the material can no longer withstand the applied stress and experiences a sudden loss of structural integrity, resulting in complete failure or fracture. Let us take each region of the stress-strain curve and know some key points. To be clear, let's divide the stress-strain diagram into 5 regions. Consider O region. It is elastic region. In the elastic region, the material behaves elastically, which means it exhibits linear deformation. When a force is applied to the material, it deforms proportionally and recovers its original shape when the force is removed. The stress-strain relationship is governed by Hooke's law, which states that stress is directly proportional to strain within the elastic limit. The slope of the curve in this region represents the material's elastic modulus or Young's modulus. In general, the point that we have to know in this region is 1. Stress is directly proportional to the strain. 2. Hooke's law is valid in this region. 3. The slope of the line O is called the modulus of elasticity, and it is constant. Consider a D region. 1. If the bar is unloaded before elastic limit point B, it will instantaneously regain its original shape and dimension. 2. The rate of increase of strain is more than that within the proportional limit. 3. The upper yield point at point C is the stress level just before yielding starts, and the lower yield point at point D is the stress level at which yield is maintained. 4. In this region, the volume of specimens increases, and this volume change is associated with normal stress. Considered a region, which is considered as plastic region. In the plastic region, the material undergoes significant plastic deformation with increasing stress. The strain increases without a corresponding increase in stress, indicating that the material is undergoing permanent deformation. The stress-strain curve shows a gradual increase in strain with relatively constant stress. The slope of this region is called the plastic modulus. In this region, 1. The strain increases with the significant increase in stress. 2. Elongation of the bar is due to the slippage of material on an oblique plane. Hence, shear is responsible for the elongation. Elongation due to shear will not lead to any volume change. 3. Hence, there is no volume change during plastic deformation. Note, shear stress is maximum on the 45-degree plane. EF region. 1. It is the strain hardening zone. 2. In this zone, the material starts offering resistance against deformation. This is because of a change in the crystalline structure of mild steel. FG region, which is the necking region. Necking occurs in certain ductile materials when they are subjected to high tensile stresses. It is characterized by localized deformation and narrowing of the cross-sectional area of the specimen. Necking typically occurs after the ultimate tensile strength is reached in this zone. 1. Necking happens. 2. F is the ultimate stress point. 3. Localized instability creeps in, and the cross-section of the specimen at some locations begins to decrease, and ultimately, at Chi fracture occurs. It's important to note that the strain-stress diagram can vary depending on the material being tested and its properties. Different materials, such as metals, polymers, and ceramics, exhibit different behaviors and have distinct stress-strain curves. The diagram provides valuable information for material selection design and understanding the mechanical response of a material under different loading conditions. Engineering stress, strain versus true stress strain. True stress strain and engineering stress strain are two different approaches to describing the relationship between stress and strain in a material during deformation. Differences and relation. The main difference between engineering stress, strain and true stress, strain is that engineering stress, strain assumes a constant cross-sectional area and length throughout deformation, while true stress, strain considers the changing dimensions. During plastic deformation, the cross-sectional area decreases due to necking, resulting in an increased true stress compared to the engineering stress, which remains constant. Thank you for watching the video. Don't forget to like, share, and subscribe our new channel. Have a nice time.